I'm Luke Seibold, you're watching PhyziX, and this is the kinetic molecular theory. Energy comes up throughout physics, and even in thermal physics, and this is because temperature is actually a measure of the amount of thermal energy that something has. Now, something that is warmer or has a higher temperature will have more thermal energy, while something that is colder or has a lower temperature will have less thermal energy. And thermal energy is always moving around a system and being transferred until what is known as thermal equilibrium is achieved. So this can be illustrated by imagining we have one box filled with a bunch of hot air, and then another box that's filled with a bunch of cold air. So here are two boxes, one that has a very high thermal energy and one that has very little thermal energy. And so because thermal energy is always being transferred to create a thermal equilibrium, or where the thermal energy is all equivalent within the system, all that thermal energy is going to move from where it's at its highest, and some of it is going to go to where it's a little lower to balance it out throughout the system. And then we're going to have one system with a balanced thermal equilibrium where the thermal energy is constant throughout the system. So we have a balance of the two levels of thermal energy. So in classical physics, we have three states of matter, and these three states of matter are gases, liquids, and solids. These three states of matter are defined by the amount of kinetic energy that their particles have, and that's why this is called the kinetic molecular theory. So gases will have the most kinetic energy in their particles, and so they're going to be moving very fast with a lot of energy all over the place, vibrating, moving super fast. Whereas liquids will have little less kinetic energy and they'll be much closer together. They'll still be pretty randomly placed and moving all around one another. Now, solids have much less kinetic energy, and so their particles remain basically in place, except they do vibrate and move around a very little amount, but for the most part they're in a pretty solid, organized structure that doesn't allow them to move very much. Now this is why gases will fill whatever container they're in. So they will fill whatever system they find themselves in. There's no fixed position of how they will be arranged. Should I say no fixed position? And there's very weak intermolecular forces. Now, intermolecular forces are the forces that are pulling these particles together, and as they're very far apart, the intermolecular forces will be very weak. Now, liquids will have a fixed volume, so they will fill the shape of whatever system they are found in, but they won't ever grow or shrink in volume. However, they can change shape to match whatever container or system they find themselves in, and they will have a stronger or intermolecular force than gases. And the particles will still have some movement. Finally, solids will have a fixed volume as well. So they're not going to increase in volume or decrease in volume. They will have a fixed shape. They're not going to change shape like water does to fill whatever system they're in. And they will have very strong intermolecular forces. And so, as we talked about before, 0 Kelvin is where the particles will have no energy whatsoever, and this is only theoretically possible. So the particles in a solid will still be moving very slightly, but they'll only be vibrating. Now, if you've ever boiled or frozen water, you'll know that different substances can actually change the state that they're in. And this is because they're given more energy or energy is taken away from them so that the particles either have more energy or less energy, making them characterized as a different state than they originally were. So we're going to take a look at what some of these energy changes are called. So let's imagine we give some energy to a solid until the particles take on the characteristics of a liquid. They start to move around a little bit more and become a liquid. This is what's called melting. So that's pretty easy to remember. When a solid melts, it becomes a liquid. And if we give it some more energy, the particles then begin to take on the characteristics of gas. This is called evaporation. Because when liquid evaporates, it becomes a gas. Now, let's say we were to take away that energy from the particles in a gas so that it becomes a liquid. Now, this is what's called condensation. And so this can be seen when a gas comes in contact with a cold surface, like a cold window or something, and the gas condenses on the cold surface because the energy is being taken away from it by the cold, and it becomes little water droplets on that glass. So that's called condensation. Yeah, a little S there. Condensation. So now if we take away even more energy from the liquid until it becomes a solid, this is what's known as freezing. And again, easy to remember because when a liquid freezes, it becomes a solid. So how do we go about measuring temperature? Well, you may have heard of the Celsius system. And the Celsius system is based around the boiling and freezing points of water. So we decided that at 0 degrees Celsius, water would freeze, while at 100 degrees Celsius, water would boil. Our standard unit in physics for temperature is actually the Kelvin. And the Kelvin is actually pretty similar to the degree Celsius in that each unit Kelvin is the same as each unit degree Celsius. So the difference between 0 degrees Celsius and 1 degree Celsius is the same as the difference between 0 Kelvin and 1 Kelvin. Except the difference is that they're offset by 273 degrees. This is because Kelvin is an absolute measure of the amount of energy that a particle has. So at 0 Kelvin, the particles will have 0 energy. They won't be moving at all. This is an entirely hypothetical situation, but it's what 0 Kelvin would represent rather than the freezing point of water. And the point in Celsius at which this would actually occur is at negative 273 degrees. So Kelvin is actually equal to Celsius plus 273 degrees. And that's how we convert between Celsius and Kelvin. And there you have it. That's the essence of the kinetic molecular theory.